Szabó-Bárdos, and the two referees, Dr. Emília Tálas and Professor Attila Demeter. Both of them are from the Institute of Materials and Environmental Chemistry, from the Research Center for Natural Sciences. So please, Mr. Wafi, start your presentation and try to summarize your results briefly.
Okay, thank you very much. I'll try to share my screen first. Okay, sorry about this one. So now everybody can see my screen?
Yes, for me it's okay.
Yeah.
Okay, good. I'm sorry. Okay, thank you very much for the time and everybody to my pre-defense presentation. Today I feel honored and really happy to present you my dissertation about the preparation and characterization of the nitrogen dioxide for the photocatalytic degradation. Before do that, I would like to thanks to my committee member, Professor Rita, Földes, Dr. Emília Tálas, and Professor Attila Demeter for all support, comment, remarks, improve my dissertation. This is my outline of the presentation today. I will start with the introduction, experiment, thesis point, and the last conclusion. Nowadays, we have a great challenge in the environmental issue, especially in the surface water, which have been contaminated with the several toxic materials, including pharmaceutical, dyes, pesticides, or even bacteria. Several methods have been used to tackle this problem, including the photocatalysis. This method is able to produce the oxidative radical, which can decompose contaminant or the pollutant into a harmless product, even at the lower concentration. So this the general reaction of the heterogeneous photocatalysis, when the semiconductor or catalyst is illuminated with by light, the electron and hole produce and migrate on the surface of the catalyst. But in the same time, this charge carrier may recombine each other both inside or on the surface of the catalyst. So the electron on the surface of the catalyst can react with the oxygen in superoxide anion radical, and hole react with the water producing hydroxyl radical. This active species then attack the pollutant for mineralization process. There are some there are some type of the semiconductor in this purpose, but it should be taken into consideration that its band edge position should be suitable to produce both hydroxyl radical or superoxide anion radical. So in this case, titanium dioxide is a good photocatalyst. Besides that, this material also easy and relatively low cost and high stability and non-toxic in the environment. However, this material can only be activated under UV illumination due to its wide bandgap energy. And in addition, the fast recombination of the charge carrier is also the disadvantage of this material. Therefore, to tackle this problem, our goal is to modify the titanium dioxide with the different elements such as metal or non-metal element. Firstly, we modified the titanium, the nitrogen, to reduce its bandgap energy and then extending its light absorption into visible region. To overcome the fast recombination process, the silver modification, the silver nanoparticle was attached on the surface of the catalyst to capture the photogenerating electron and then the lifetime of the charge carrier. Besides that, the presence of the silver nanoparticle on the surface of the catalyst is also expected to inactivate the microorganisms such as bacteria. Another important goal of our study is to evaluate the coumarin with the different species. Coumarin can react with the hydroxyl radical, producing several hydroxycoumarin. However, only 7-hydroxycoumarin can be detected by luminescence method. In addition, coumarin also react with other species producing non-fluorescent product. To investigate the photoactivity in the pharmaceutical contaminant, we use the hydroquinone as a model compound because compare dyes, which in the dyes model compound can absorb the light and interfere the photocatalytic performance. So this is a good model compound to study the photocatalytic activity of the prepared catalyst. We have three different methods. Firstly, we use UV light as a light source, and then the other two are with the visible illumination but with the different arrangement. In this case, we change the arrangement and the position to increase the light intensity and then the photoactivity. This is our first thesis point. The dosing order of the precursor and the calcination temperature significantly affect on the morphology and the photoactivity of the catalyst. From this same image, we see that at the first dosing order, firstly we added the titanium precursor and the nitrogen precursor. We got the non-hollow structure, but if we change the order, which the nitrogen precursor first and then titanium precursor, it produce the hollow structure with around 2 micrometer diameter. But all of this material are in the irregular shape or in a microparticle around 2 until 100 micrometer. We also study the photocatalytic activity of the cut in the coumarin solution, and then the production of the 7-hydroxycoumarin was detected by the lumination method, and then from that we calculate the initial rate of the 7-hydroxy formation. We see here that in all, we also optimize the synthesis here. In all cases, in all synthesis temperature, the second dosing order was produce more 7-hydroxycoumarin compared to the first one. And then we got the optimum condition at the second dosing order at 10 degrees Celsius for the synthesis temperature. And then condition we use for the further experiment. From that, we compare the photoactivity of our catalyst with the different catalysts like undoped titanium dioxide and then the gusa as a standard one. We see that our catalyst perform the best photoactivity under visible illumination. To study the effect of the calcination temperature, we calcine the catalyst at the different temperature. From this result, from the XRD result, we see that up to 350 degree, the catalyst consisted anatase phase, and but different crystallite size. The FTIR spectra show a typical peak after nitrogen modification in two areas. The first one at around 1,400. This is a new peak. This is the undoped titanium. But after nitrogen doping appeared a new peak here. And the second one around 3,000 centimeter. So these two peaks indicate the NH bending. In this case, is in 1,400 NH bending, and this here is overlapping with the hydroxy group. To see or to study the effect of the calcination temperature on the photoactivity, or we make this figure that it clearly see that under UV the photoactivity increase upon the increasing calcination temperature. It strongly relate to the crystallite side, which the higher calcination temperature, we got the high crystallite side and also the photoactivity. Under UV illumination, the band gap energy relatively did not affect on photocatalytic activity, because the UV light is the energy of the UV light is enough to activate the catalyst even at the higher band gap energy. However, if we see under visible illumination, beside the nitrogen content should be maintained to remain in the catalyst, because it affects on the band gap energy and also the efficiency of the light absorption under visible illumination. In this case, we got the optimum condition at the 450 degrees Celsius. From this point of view, both crystallite side and the nitrogen content played a crucial role on the photocatalytic activity of nitrogen doped titanium dioxide. Our second thesis point is the specific surface area play a crucial role on the photocatalytic performance of titanium dioxide. We prepare another nitrogen doped titanium dioxide with a different method and the different nitrogen source, and then we compare both the catalysts. From this figure, we see that the N-TiO2 catalyst, or the nitrogen doped titanium dioxide prepared with the solvent method, produce a non-hollow structure. However, with the NT produce the hollow structure. This morphology is really correlate with the specific surface area, that with the non-hollow structure, NTU lower specific surface area compared to the NTA catalyst. Even both of them are in the anatase phase. We also study the photocatalytic activity in the coumarin solution. From this figure, we see that with the hollow structure of the produce a higher 7-hydroxy coumarin and also a higher coumarin degradation. This better performance may be due to the hollow structure and also, as we mentioned before, a higher specific surface area. The third thesis point is the effect of the silver modification on the photocatalytic activity and the antibacterial activity depending on the surface morphology. We see that both catalysts then we modified with the silver nanoparticle, and then for the N-TiO2 catalyst, the photoactivity could be by silver modification until the optimum concentration. But in contrast, for the NTA catalyst, the silver modification was not perforable for the photocatalytic activity. It may be due to the different morphology of about catalyst. It also can be seen in the specific surface area that for the N-TiO2 catalyst, the specific surface area increase after sulfur modification. However, for the NTR hardly change or relatively stable even after modification. This probably on the non-hollow structure of the N-TiO2, the sulfur nanoparticle attached on the surface of the catalyst with the smaller, but for the NTR, the sulfur nanoparticle agglomerate and with the higher size and also attached inside the hollow structure. The antibacterial activity show that compared to the control which obtained from the market, the N-TiO2 catalyst, the sulfur N-TiO2 catalyst in this concentration relatively similar with the control. However, for the NTA was smaller compared to the control. But both the sulfur modification proved that to enhance the photocatalytic, the antibacterial activity compared with the unmodified one. The fourth thesis point is coumarin can be used as a single chemical probe to detect both formation of the and other active species. As I mentioned before, that the coumarin can react with the hydroxyl radical, producing 7-hydroxycoumarin. From this data, we can estimate the production of total hydroxycoumarin. It indicates the coumarin, the product of the hydroxyl radical, or the coumarin reaction with the hydroxyl radical. So the difference between the total coumarin degradation and the hydroxycoumarin produced indicate the coumarin reaction with other species. So from this figure, both in the anaerobic or aerobic condition, the coumarin reaction with other species was higher compared to the coumarin reaction with the hydroxyl radical. Under anaerobic condition, in the absence of the oxygen, the coumarin reaction with the other species mean that the coumarin reaction directly with the photogenerated electron. However, in the presence of the oxygen, coumarin can react directly with the electron, or coumarin can react with the superoxide anion radical. But if we take the reaction rate of the oxygen with the electron is higher compared with the coumarin reaction with the electron. It means that in the aerobic condition, the coumarin reaction, reaction with the superoxide anion radical compared to the coumarin reaction with the electron. So when we apply this method into the sulfur modification of the nitrogen titanium dioxide, we see that in the N-TiO2 catalyst, the presence of the sulfur nanoparticle change probably doubled the coumarin reaction with the hydroxyl radical or with the other species. However, for the NTR catalyst, relatively not change or not favorable for the photocatalytic enhancement. The fifth thesis point, instead of dyes, the colorless hydroquinone proved to be a promising model compound for the photocatalytic experiment under visible illumination. In the absence of the catalyst from this figure, in the absence of the catalyst, we see that the hydroquinone concentration was stable during the experiment, but when we put the catalyst on the photocatalytic experiment, the hydroquinone was totally decomposed after around 4 hours. The tendency was similar in case of the coumarin, in which for the N-TiO2 catalyst, the photodegradation of the hydroquinone could be enhanced by silver modification, but no different for the silver N-TiO and the N-TiO catalyst. Besides the measuring the hydroquinone concentration, we also measure the TOC concentration during the photocatalytic experiment, and it was in line with a feature that the TOC reduced during photocatalytic experiment. It means that the mineralization occurred during this experiment. If we compare the ratio of the hydroquinone degradation in the coumarin reaction with other species, we clearly see that the ratio both N-TiO or the N-TiO is similar. It means that the other active species play a crucial role in the degradation process of the hydroquinone instead of the hydroxyl radical. To sum up this presentation, firstly, the nitrogen titanium dioxide with the hollow and hollow structure was successfully prepared with the different methods which are active under visible illumination. The surface structure, crystallinity, nitrogen content in the specific surface area were found to be a crucial feature in the photocatalytic activity. The silver concentration also should be controlled for the to enhance the photoactivity or antibacterial activity. The photocatalytic pathway show that the coumarin degradation through the reaction with the other species were more efficient compared to the hydroxyl radical, and the hydroquinone was effectively decomposed over the prepared catalyst. These are the paper we have published during my study, and I involved in the several conference also presentation and poster presentation. And before I finish this presentation, I would like to thanks to my supervisor, Dr. Ottó Horváth and Dr. Erzsébet Szabó-Bárdos, who have been helping me during my study. And also thanks to all people contributing in this work, and all funding we obtained. And then thank you very much for all staff and colleagues in this department or research group. Thank you very much.
Thank you very much for the presentation. And I just noticed that Orsolya is recording this session, so I hope all the people present agree to this recording. I'm sorry, I should have asked it before, but I didn't notice it. So I hope nobody has an objection against the recording of the session. I do not see any objections, so thank you. So first of all, I would like to ask Dr. Emília Tálas to present her evaluation and to ask the questions from Wafi. Please, Emília.
Okay, thank you. Do you listen me?
Yes.
Okay, so first some general comments. That the thesis presents original research results in the field of photocatalysis. The amount of the work is sufficient, the results are interesting, and the thesis is based on 2 publications in high-quality peer-reviewed journal, where Abdul Wafi is the first author. So this meets the expectation of the doctoral School of Chemistry and Environmental Sciences of University of Pannonia. However, I suggest improvements in the wording of the dissertation at several points. First, some general comments. In my opinion, the objectives are clear. The topic is interesting and actual. The literature review has a very logic structure. It is comprehensive, intensive, critically evaluated, well related to the work presented in the dissertation. The experimental part is sufficiently detailed, and the method used to prepare the photocatalyst are relatively simply. The starting materials are relatively inexpensive, so these are very advantageous for practical implementation. The chosen methods of physical chemical characterization well suited for the analysis of the prepared samples. The photocatalytic measurements were well planned and carried out carefully. However, the results and discussion section, especially its editing, leaves too much to be desired. The main problem is, at least in the first version, that the grouping and presentation of the data does not correspond to the chapter titles. Subsection 5.1 titled Anti-A-catalyst deals with the preparation and characterization of ammonium-doped titanium. This part is followed by the subsection 5.2 entitled Anti-U catalyst, which is urea derived sample. However, the second chapter presents again lots of results obtained about the ammonium-doped titanium. Therefore, I think the line of thought is confusing. And in my opinion, the data for the two samples should be separated and new figures should be created, or the structure of the discussion presented in the table of contents should be changed. I don't know. You answer now or later?
Should I answer now?
Yes, I think so. Please, Wafi, answer and then please question.
Okay. Yeah. First of all, thank you very much for the reviewer for the valuable important remarks and opinion and also a question to improve my dissertation. And for this case, I have restructured and then regrouped the result into one chapter regarding the regarding on the catalyst. For instance, the NTA result removed from that chapter 5.2, and then we move to the NTA chapter 5.1, and then we make 5.2 purely into catalyst, and then we already modified this chapter in the current version.
Okay, thank you. Now the second comment, that it is enough to enter the data in one version. It is unnecessary to enter the same numbers in the tables and figures and even to enter them into the text. Some example, figure 5.15, table 5.3, and the text on page 56 is the same. And again, figure 5.17 and table 5.4 and 5.5 is the same. So it should be decided how the data will be presented in table or in figure.
Yeah, we also modify this, the repetition or duplication also. For instance, we remove some text in around page 54 and 68, and also we remove the table 5.2, 5.3, and then some features also, and then we adjust the residual text after modification.
Okay, thank you. And my problem was also that I felt that the wording was not completely good in several places. Literature citation to explain the own observation and literature citation to support the own conclusion should be worded in such a way that can be clearly distinguished from the own work. I wrote some example, and after this example, I felt that the sentence were meant to be an explanation, but I suggest in the results and discussion it's much better to start a sentence that all results obtained on nitrogen doped sample was in line with the literature and so on.
Yeah, we already we also modified that kind of the word. The wording with such our line is in line with the previous literature or something like that. We modified that sentence.
Okay, thank you. And just one small comment that if you introduce the abbreviation used everywhere. So I found when ROES was not used.
Yes.
Other notes and questions. Page 42, 43, that's DT analysis, and figure 5.3, that's you showed the figure and you wrote in the text that the catalyst, these two samples behave differently, but it would be good to get explanation why they behave differently. What's the reason?
We as I mentioned before, we restructure the content of the dissertation, and then we separate both NTA and the NTU, so it's easier to explain. And then we also extend the explanation about this thermal analysis. And then regarding the question also, yes, the starting material was after drying at the 400 degree for 24 hours. So this is the starting material for the thermal analysis.
That was the question that it would be nice to write even in the figure caption what was the starting point and where it is going. And also page 45. That's the formation of the hollow structure is very interesting, and it's important because of the high surface area, specific surface area, and I thought it would be good to get a more detailed explanation why this depends on the dosing order.
I will share my screen. Probably it's better if I answer. So, okay, this is the question. Okay, regarding this this question, we have modified in the current version to a detailed explanation about the why it's produced the hollow structure. So in this case, generally in the first dosing order with titanium precursor, and then the last is the nitrogen precursor. The titanium precursor was firstly hydrolyzed with water, and then in the strong acid to form titanium ion. And then the second hydrolysis was occurred in the presence of the ammonium solution, and then producing a milky solution. And then after that, the precipitation. However, for the second dosing order, this solution, we mix it firstly, and then the last step was the titanium precursor addition with the dropwise method. So when the titanium precursor was slowly dropped, basic solution, so the solution was the basic solution because the volume of the ammonia was more than the nitric acid. pH should be around 11. So when the titanium precursor was slowly dropped into the basic solution, the hydrolysis reaction would rapidly occur on the surface of the droplet, like in this figure. So the original droplet fragmented in the smaller droplet due to the surface reaction induced acting force on the droplet and the gravitation. Then after, the titanium cell layer will be formed, and then after that, because there is a reaction on the surface of the droplet, and then the titanium cell layer will be formed on the surface of the droplet, the small droplet, due to the surface hydrolysis reaction, and then leading to the surface hardening of the drop. Because of the significant density between a solid titanium dioxide on the surface and this is in the center is a liquid, so the liquid will release and then form the cell hollow structure.
Okay, thank you. It's really very nice and very interesting. Let's go further. That it was written on page 53 that the large crystallite large size provided better absorptivities, thus inducing a higher photoactivity. So as I understood well, the increased activity was the reason of the increased activity was just the crystality that was mentioned. But I think the explanation should be made a little bit nuanced, because the defect site of the structure of the sample treated at high temperature is also more perfect, thus containing less recombination centers, which has also a positive effect. So this is reflected in the use of UV radiation. However, the nitrogen content decreased in parallel, so consequently the activity in the visible range decreased. So
okay. It's true that at the higher calcination temperature, with the higher crystallite site, also the defect is smaller than at the lower concentration, which is effect on to lowering the recombination center. So we modify that to extend this explanation on the dissertation also. Thank you very much for this.
Okay. Now, some comments on page 54. It's again a repetition. That sentence which is written starting with coumarin can react with and so on. It's completely the same as written in figure 3.9. So that's somehow again or to remove from
we remove the sentence because it's repetition in the probably in the literature review. So we remove this sentence in current.
Yes, page 62. It's again about an explanation. Yes. So again, that comment that it should be noted that the sample constant higher temperature has fewer defect sites.
Yes.
I think recombination center.
We also modified this.
Yeah. And page 63. Yes, it can be read that strong exothermic peak about 400 degrees observed for both N-TiO2 and N-TiO samples. It can be assigned to crystallization process and phase transformation of amorphous anatase. So my question was that based on above sentence, can it be said that in case of undoped titania, where this peak is missing, there is no amorphous phase at all? And another question, do you know any literature example that the doping element significantly influences the crystallization?
For this question, actually in the thermal analysis for the undoped titanium dioxide, there is probably a low and broad peak observed on the around 400 degree Celsius, but not as sharp as in the nitrogen doping. Probably with the low and broad peak for the undoped titanium dioxide imply that the smaller part of the catalyst may transform from the amorph to anatase phase. Then if we check the measurement, we try to compare for the undoped and the nitrogen doping, we see that for the undoped titanium dioxide possesses a smaller intensity in this case, and also the crystallite site compared to the N-TiO2 catalyst calcination temperature, in this case 450 degrees Celsius. This means that the doping with the element may affect on the crystallization process. And also, there are some literature evaluating the effect of the doping element on the crystallization process. For instance, I mentioned Albert and Lowe reported that aluminum doped titanium dioxide could accelerate the amorph to anatase phase transformation at the lower temperature compared with the unmodified one. And also, Swanarwang et al. Mentioned that the incorporation of the nitrogen into titanium dioxide could prevent or delay the fast transformation from anatase at high calcination temperature compared to the pure titanium dioxide, as we see in this figure.
Oh, okay, thank you. I also have an example in my practice. The tin as a doping element also decreased the temperature of the rutile formation. So in that case, the main reason is that the tin oxide has also the rutile type of crystal, and it's behaved like a seed for rutile formation and for the phase transform.
Yes.
And let's go further. Yes, page 68. There is a sentence about silver deposition, which, in my opinion, in that form fit better to the literature review than to the results and discussion.
Yes, I agree. We also removed this sentence from the result, and this we moved. Probably it already mentioned in the literature review, so we removed this.
Okay, thank you.
Thank you.
And page 69, that's a question that what is the reason for the different absorption of silver ion on different on titanium samples prepared by different methods?
Yeah, the different absorption of the silver ion in the ICP measurement between two samples can be attributed to the different morphology, where the NTA catalyst with the hollow structure could absorb silver compared with the non-hollow structure. So it's due to the surface characteristic of the hollow structure favorable in this respect.
I understand, but that was interesting when you finished the whole procedure, the total silver content was very similar.
Oh yeah, because the concentration of the silver was very small, if you see. So after UV radiation, the all silver content was maybe deposited on the surface of the catalyst, because it compared to the catalyst, its concentration are very small.
Yeah, so it means we have to imagine this process that first step is adsorption, after that there is a reduction, and again reduction because the UV light.
Yeah, if we can imagine that the first adsorption, because we stir it before the irradiation, we stir it to homogenize this mixture. In the adsorption of the silver ion, still in the ion, but after starting the UV illumination, this absorbed or ion reduced to the silver 0, and also there is another adsorption maybe during this UV illumination. I mean, the following adsorption occur and then reducing also, because the concentration of the silver is very small.
Yeah. Okay. Thank you. Yes. Page 75. One comment that figure 5.26, which is a very nice figure, but I wasn't able to find which sample.
Oh yeah. This I also already put the concentration on that figure, so it's about 10 minus 5 per gram.
Okay, and page 72, and that was the question that can you imagine any kind of dissolution which contribute to the increasing of the surface specific surface area?
In this case, because the titanium dioxide is very chemically stable material, even after nitrogen doping, the dissolution on the surface is particle, so it's need to be in the extreme condition, maybe mostly in the cases.
Yes, I understand, but I know that titanium is quite stable, but I thought maybe some inorganic or organic residue which can be dissolved, some kind of alkali oxide or something.
Because we use the nitrogen of titanium dioxide, it's
nothing.
Just dissolved in the water in the presence of the silver element. So probably I'm not sure that there is a dissolution.
Okay, thank you. And was again with the specific surface area that does the different size of the silver nanoparticles and the different particle size distribution contribute to the different changes of the specific surface area?
Yes, I agree that the particle size and also its distribution also contribute increase the specific surface area. It's well known that the smaller particle size lead to the larger specific surface area. In this case, from the time measurement indicate that the size of the silver nanoparticle on the NTU was significantly smaller with the catalyst. In the NTA, it's about 100 micro or 550 micro, but in the NTU catalyst, it's some of them even smaller from 50 micro. Micro or nano. So a higher silver at the NTA, a higher silver agglomeration may occur in the NTA catalyst. However, in addition, the different morphology of two samples may be crucial on the different change of the specific surface area during the silver modification. The surface area of the hollow structure could easily be enhanced by introducing silver nanoparticle on the surface with the smaller particle size, maybe with the smaller particle size and also distribution. But with the NTI catalyst, we consisted like the hollow structure, and probably the silver nanoparticle attached on this wall, in the wall of the hollow structure, maybe inside the hole. So it's hardly to change the specific surface area. I think.
Okay, thank you. And at the end, just I have to tell that I accept this the thesis point, and after correction, I recommend the submission of the dissertation. Thank you.
Thank you very much.
Thank you very much, Emília. And now I would like to ask Professor Attila Demeter to present the evaluation and put the questions to Wafi.
Okay, so my report will be more consistent if I read at least the beginning part, and after I will neglect or quick some less important comments. So the dissertation with some smaller modification is suitable for submission as the following step of the PhD thesis. The English is quite acceptable, pardon? Understandable is clear, very few. 92-page text contains approximately 52 well-made figures and 13 informative tables. The dissertation is based on 2 articles. In both, the first author and those published in proper, reasonable journals. Similarly, the dissertation also consists of 2 separate but cohesive parts, with each feature is proper for a PhD. The text quotes 187 references.
Hello.
There are 5 statements. Must be emphasized, research is reasonably better than most of the studies in the literature. There are a lot of widely
Hello.
growing acceptance. Choice titanium dioxide invisible, while makes steel simple. This the points, the thesis point seems to proper and acceptable for me. So, next section, maybe too much.
Hello.
I have very, I don't like it. Okay. So I have three main comments. The first one, I suggest a little bit my time game. The study to improve the knowledge of the
Hello. I cannot hear clearly.
Yes, Professor Demeter, we hear you very, very poorly. Sometimes
there is noisy.
There seems to be no connection, and there is some noise.
Microphone is on, so if you switch is on, the microphone maybe will be less. So it is not. I need to switch on. Okay, so the first point I put less effort. That is photocatalytic. It's quite even the problem is that the water purification. There are several sites dust clean this very different. I don't think so. The second question is interesting. I think in the corresponding chapter it would be good that it is that and emphasize even in the lecture we have learned here that what is the electrical process. So that we see that in page 7 that the oxygen reduction is around 3.08 electron volt, and it is just the range of the titanium dioxide band gap. So if we decrease the band gap, it seems that
Professor Demeter, we hear you very poorly, so I would like to ask Wafi to turn off my microphone. Please try to mute it.
Hello, sorry.
No, I have not heard. Maybe Abdul microphone would be switched off or temporarily that we can try it.
Yes, so please, Wafi, try to mute yourself, try to turn off your microphone, then it might be better. And then you can turn it on when you will answer.
For me now is much better. So okay, so for me it's now is quite okay. Okay, so in these questions rise the same problem which I mentioned in this my opponent, that literature value is very problematic because everybody used not only different lamp but different model compounds, and the different model compounds have different oxidation potentials. So its comparison with this data is almost tell nothing. So it is a question for me. For example, it raised when I heard this presentation that how much coumarin or hydroquinone oxidized on the holes in the anode part, but it's not really time to go deep in it. Last problem group, which is I have seen in the answer of my questions that he solved it and would be good to include in the PhD thesis, or not the thesis group, but the lecture part, that would need some stronger references as quantum yield, for example. So I leave out the small points, except two, maybe the 15th and the 18th point. 18th points also, of course, the silver is trapped the electron and improve the lifetime of the charge separation, but it's also changed somehow the exchange current, because which is somehow belongs to the absorption of the corresponding species, present case probably in the oxygen in the cathode, because the oxygen reduction occurred there. He can think about it, whether it's include or increase some part in explanation. A last thing I would like that tell, even in the answer of the my report, is some number is contains too much digits, so it's not so good, and it's somehow disturbing that some value is given with 5 digit, or here the quantum yield is 0.09%. It's surely not better than 1.1. 1.09 is written, so I think it's 1.1 is more reasonable. There are 3 questions, and I will not read it because I think Abdul Wafi will show it, and I accept his answers, but better to if he tell us here also. Okay, but it's related to what I have told before. Okay, so I now switch off my.
Okay, so Mr. Wafi, please answer the questions. So I hope you put the questions to your slides also, as in case of Professor Tálas. So I will ask you to answer the questions of Professor Demeter.
Okay, thank you very much. And first of all, I would like to thank to the Professor Attila Demeter for the all the opinion and remark to improve my dissertation. We have all emphasized also the objective, in this case, some remark objective about the material modification of the titanium dioxide, and also mention it's the drawback of the heterogeneous photocatalysis in the literature review. Regarding the density or the electrochemical point of view, we to add one sub-chapter about the fundamental semiconductor. In the current version of the dissertation, we explain about the Fermi level and in the both extrinsic and intrinsic semiconductor, and also the semiconductor electrolyte interface reaction. So also, yes, for the quantum yield, we have estimated the quantum yield, especially for the Degussa, and also we compare with other catalysts, both before sulfur modification and then after sulfur modification. We already put on the current version of the dissertation. And regarding the specific question, we try to calculate the quantum yield, in this case for the Gusa, under UV illumination. Primary quantum yield we can calculate with this equation, and in this case, in the first step of the reaction, the reaction of the photon in the titanium dioxide produce the hydroxyl radical, and then this hydroxyl radical attack the coumarin. First step produce the hydroxycoumarin radical in this like here. So this hydroxycoumarin radical react each other, producing the hydroxycoumarin and the coumarin compound. So this is probably the very primary quantum yield of this reaction. And we also calculate the overall of the quantum yield with this we obtained from the previous literature in here. So this is the calculation of the quantum yield for the Dagusa under UV illumination, and then we got around value 1.1 percentage of the total. We are from this value we compare also with the undoped and the nitrogen doping, and in which it's obviously it's lower than this value, because as we have seen in the Dagusa was the highest one in the UV illumination. Regarding the second question, and how many cows in phase transformation white loss, so around 400 degrees Celsius in the thermal analysis, we see a white loss there. So it's indicate to the release of the oxygen here, because this is in the arm, and then during the heat treatment forming the intermediate and water here. So this one oxygen release for the restructure the crystal of the titanium dioxide, and then release the water, and then form the anatase phase. So the weight loss around the 400 degree in the thermal analysis can be attributed to the loss of the oxygen from the amorph titanium, while the anatase formation. And then the third specific question is, do you see any further step with the nitrogen of titanium dioxide which may improve the photocatalytic parameter? And I realized that the drawback of this material is its irregular shape and relatively larger particles, because which are very important in the photocatalytic activity, especially in the specific surface area. So in the optimization of the different parameters, such as hydrothermal or sulfur thermal, may be one option to obtain the uniform shape with the smaller particle, because I read some article with the hydrothermal, for example, they got the smaller nanoparticle with the uniform shape. In addition, the optimization of the nitrogen concentration also seemed to be a promising to obtain the optimum condition regarding the photoactivity. That's all. Thank you.
Well, as I have told, I accept the answers and suggest at least the 2 points include some shorter paragraph into the text when it is proper. Okay.
Okay, thank you very much. So I would like to formally ask the referees if they accept the answers and if they have any further questions.
Yeah, I accept and I have no further question.
No, neither me. And as I told, I accept.
Okay, thank you very much. And now I ask the audience if they have any questions or comments. Probably the supervisors might add something, a comment or something like that. Professor Horváth, please.
Yeah, thank you very much. I just like to say also on behalf of Erzsébet, Szabó-Bárdos, can we hear? Okay. So
Yes,
I
okay.
would just like to express that we have been very satisfied with the performance of Mr. Wafi. He has been very dedicated regarding his PhD work, both in the aspect of learning and in research work. So he was very flexible and creative. If he had to modify something regarding the structure of manuscripts, etc., and regarding the types and methods to be applied, he was very, how can I say, initiative and thorough enough, especially step by step. He got into the important details of the experimental works. And after that, the theoretical evaluation and the compilation of various manuscripts involving PhD thesis. So I would like just to thank him for his really detailed and, how can I say, satisfactory work. Thank you very much.
Thank you.
Thank you very much. And if there are no further questions and comments, then I think we should have a formal decision that the thesis, of course, after the necessary improvements, can be submitted for further processing. So, do you agree with that?
Yes, I agree.
Yeah, I also.
Okay, thank you very much. And at the end, I would like to thank the referees for the work and Mr. Wafi for their presentation. And I wish him feel a lot of success in the future. So thank you very much for taking part in this pre-defense, and goodbye for everybody.
Thank you very much.
Thank you. Bye.
Okay, goodbye.
Goodbye.
Köszönjük szépen!